Let's take a very quick look at protein synthesis. Now, we know DNA is the hereditary molecule. It's also known as the information molecule. It has all of the information to code for making proteins. But how does that happen? Because the DNA cannot leave the nucleus, and proteins are made at ribosomes out in the cytoplasm. Well, what happens is DNA is used to code for an RNA molecule, a messenger molecule, which can then leave the nucleus and take that information out to the ribosomes to make the proteins. Let's just have a really quick look. We start with our double-stranded DNA molecule, and that gets opened up in much the same way as for DNA replication. DNA polymerase 3 would come down and replicate the DNA. Well, in this case, instead of DNA polymerase, we have RNA polymerase because we're making an RNA molecule. The difference between RNA and DNA, well, there are a few differences. One key difference is that RNA uses the base uracil instead of thymine. So you can see on this little diagram here, instead of a T, the RNA molecule being formed has a U. So it still has the other bases the same as DNA. It has A, C, and G, but it has uracil, a U, instead of the T, instead of thymine. So RNA polymerase makes an RNA molecule in a complementary fashion to the DNA strand. Now, the DNA strand that it's matching up in a complementary fashion, that is called the non-coding or the nonsense strand. And the DNA on the other side, where nothing seems to be going on, that's actually called the coding strand or the sense strand. And you can see that the RNA molecule being formed is the same as the DNA strand across the other side, except that T has been replaced with U. Now, that RNA molecule being formed, it's called messenger RNA or mRNA. That can actually leave the nucleus through the nuclear pores. Remember, there's a nuclear membrane around the nucleus, but it has these pores. Well, the mRNA can go through the pores out into the cytoplasm and go off and find a ribosome. So this is how we get the information to make proteins from the DNA out into the cytoplasm and to the ribosomes. We have this messenger molecule, messenger RNA. Now, each set of 3 bases is called a codon, or sometimes a triplet codon, because there are 3 of them. So we can see this very short piece of RNA molecule that has been formed has 5 codons. Each codon codes for a particular amino acid. Now remember, we're making proteins. The building block of protein is the amino acid. It is a polymer molecule. It's a polypeptide. It's made of lots and lots of amino acids joined together with peptide bonds. So if we take a look, we have a table like this. You can get square versions, or this is the circular version moving out that I prefer. So the first codon, I should say, we had was UAC. Now, if we start in the middle, we find the U, we find the A, we work out to the C, and we can see that the amino acid that this codon is going to code for is tyrosine. In much the same way, we follow the other codons. UUG will code for the amino acid leucine. GAG will code for glutamic acid. CUA will code for leucine. And the last one we had was UUU, and that will code for phenylalanine. So this is what we're going to end up with. We have 5 amino acids: tyrosine, leucine, glutamic acid, leucine, and phenylalanine. This is the start of a protein. Now, proteins are going to be hundreds and thousands of amino acids in length. Remember, they are polymer molecules. They are very long molecules. Now, one thing we should note is that we actually have leucine twice, but we had different codes, different codons, which both gave leucine. Well, this is because with 3 bases, we actually get 64 possible combinations. Now, that's actually needed. If we had 1 base, we could only have 4 options. If we had 2 bases, we would have 16 options. The issue is we need to code for 20 amino acids. So 1 or 2 bases is not enough. 3 bases is plenty because we get 64 combinations. So we can easily code for our 20 amino acids. In addition, it means that some of those amino acids, in fact, most of them, will have more than one code leading to that amino acid. There are actually just 2 of the amino acids where there is only one particular codon leading to them. All the other amino acids, multiple codons will give us that amino acid. So as I mentioned, this is just a very short section of what an mRNA molecule would be. This codes for 5 amino acids. In reality, a protein is very long, many more amino acids. But what happens is those amino acid chains get released from the ribosome, and we have our protein. It can go off and fold up and do its good little protein thing. Now, just to wrap up the video, I should mention 2 other terms. The first one is transcription. The actual copying of the DNA molecule is referred to as transcription. So making of the mRNA molecule, that's transcription. We are copying the information or transcribing the information from the DNA so that it can be taken out to the cytoplasm. Once out in the cytoplasm at the ribosomes, that code that was copied from the DNA is translated into an order of amino acids. So we're taking our bases and translating those groups of 3 bases into amino acids. So we have transcription followed by translation. And those processes together, of course, give us our protein.
If you like this video, punch that like button. If you want to see more videos, smash that subscribe.